Okay, so it's my pleasure today to introduce Professor Alice Shapley from UCLA. So Alice did her PhD at Caltech with Professor Charles Steido. She moved to UC Berkeley in 2003 as a Miller postdoctoral fellow. And then she became an assistant professor in 2005 at Princeton University. And she finally moved to UCLA in 2008 as an associate professor. She's now a professor and vice chair for astronomy and astrophysics at the Department of Physics and Astronomy of UCLA. She's a specialist on galaxy formation and evolution, and especially on stellar population and chemical evolution at high redshift. And today she's going to talk about the MOSFIRE Deep Evolution Field survey, MOSDEF. Alice, the floor is yours.
Great, thanks so much. And it's great to be with you. Thanks so much for this wonderful invitation. Yeah, so I'm going to be telling you about the MOSFIRE Deep Evolution Field survey, MOSDEF, or a slightly more astrophysically motivated title. I want to tell you about what we've been learning about the physical properties of galaxies at high redshift. Very importantly, I want to start off by highlighting my collaborators in this endeavor. There are several of us at the University of California who have been leading the MOSDEF survey. So Mariska Creek, Naveen Reddy, Brian Sayana, Alison Coyle, and Bara Mobasher. We also have many talented grad students and postdocs working with us in the project. Specifically today, I'm going to be showing you a lot of work from my former grad student and current Hubble Fellow, Ryan Sanders, who's just doing a lot of really great stuff. So today we're going to be talking about redshift 2 to 3 galaxies. Before we get started, I want to set the stage a bit about what galaxies are like during this earlier time, 10 to 11 billion years ago. Sometimes this is referred to as the time cosmic high noon. But why is that the case? Well, at these earlier times, we see that the star formation rate density in the universe and also the black hole accretion activity in the universe are both at their peak levels. And so if you look here in this plot over here, we see this is a graph of the star formation rate density in the universe as a function of cosmic time or redshift. And down here, we see the quasar luminosity density in the universe. And you can see that they both have activity levels that are an order of magnitude than what is observed in the universe today. And so when you look at galaxies at these early times, there are qualitative imprints of the local galaxy population. For example, we see a bimodal distribution of galaxy colors. We see also that red galaxies are more strongly clustered than blue galaxies. But there are also important differences in the observed properties of galaxies at these early times compared to what we see today. Okay, so as I'll detail in a few moments, we see that at the massive end of the galaxy population, there's much more diversity than what's observed today. We also see that while today there are dynamically cold disks like our Milky Way, such systems appear to be absent at early times. The rate of star formation in individual galaxies and their specific star formation rates are much higher at these early times. And also when we look at galaxies, we see that outflows of material are fairly ubiquitous. Okay, so I want to just go through some of these differences just so that you really have an idea in your mind about what redshift 2 to 3 star forming galaxies are like in their properties and specifically how they're different from nearby galaxies. So let's use redshift 2 as sort of our benchmark. And so one important factor is that redshift 2 galaxies are much more actively forming stars than galaxies today at the same mass. So we see over a broad range of redshifts a strong correlation between stellar mass and star formation rate. Okay, this is sometimes referred to as the main sequence of galaxy evolution. And so if this dash curve shows the relationship in the local universe, what you can see is that the main sequence evolves as you go towards higher redshifts. So the star formation rate for a galaxy that has 10 to the 10 solar masses of stars will be roughly an order of magnitude higher at redshift 2 than it is at redshift 0. Another way of thinking about this is that star formation rates of tens of solar masses per year are commonly observed in redshift 2 galaxies, while those are quite rare in the local universe. If we zoom in on the very massive end of the galaxy population, so systems that are more massive than 10 to the 11 solar masses in stars, When you look at such galaxies in the local universe, you see that they're typically quiescent, or more colloquially, red and dead. But if you go back in time to redshift 2, 10 billion years ago, you see that at the massive end of the stellar mass function of galaxies, there's still quite a diversity of systems. We see both star-forming galaxies down here and quiescent galaxies. We see a range of structural parameters of the galaxies. They're not all spheroidal. And this is a great plot from Mariska Creek, plotting each galaxy using its HST image. Another way of looking at this, a little bit more in the weeds, but just in case you care, this plot on the right here is showing the abundance of galaxies of different masses, okay? So specifically, these orange points are showing the abundance of galaxies more massive than 10 to the 11 solar masses as a function of redshift. And these blue stars are showing the abundance of star-forming galaxies more massive than 10 to the 11 solar masses. So you can see that at low redshift, the quiescent galaxies are dominating the numbers of these massive galaxies. But by the time you go back to redshifts 2 to 3, the star-forming galaxies are more numerous. So just again to say that even at the massive end, while things today are done forming stars, if you go back to these early times, the most massive systems in the universe are still actively building up their stars and assembling. Another important thing to keep in mind is that galaxies of the same mass are smaller at redshift 2 than they are at redshift 0. You can see this either in early type galaxies or in late type galaxies. So if we zoom in on the late type galaxies, you can see that a galaxy of a fixed stellar mass, its size decreases as you go back in time. Okay. Some of these effects may be less extreme if you characterize galaxies in terms of their half mass size as opposed to their half light size. But in general, I think this statement is true. Furthermore, the star-forming galaxies appear to be characterized by exponential profiles at masses above about 10 to the 10 solar masses. But at lower masses, so less massive than 10 to the 10 solar masses, the structural parameters of the galaxy seem to indicate that a lot of a significant fraction of the galaxy population may be triaxial and not disk-like. Okay, so that's sort of an interesting question that has to do with the emergence of disks. Maybe not at all masses are we seeing the disks at redshift 2, so at the low masses, things are still settling down. So more about disk-like systems at redshift 2. So if you look at some of the latest integral field unit spectroscopy, so a spectral map of galaxies, and look at the dynamical properties of late type galaxies, which you can see here on the left. So this is another plot of star formation rate versus stellar mass for galaxies at roughly Z of 2. This is from a review by Forster, Schreiber, and Weitz from just this last year. Each galaxy in this plot is indicated by its IFU map of its kinematics. And you can see that lots of these galaxies, okay, especially above 10 to the 10 solar masses, show the characteristic velocity shear that is emblematic of a rotating disk. Okay, so above 10 to the 10 solar masses, it appears that rotation is commonly observed. However, at these early times, while you may detect a rotational speed of 220 kilometers per second, like the Milky Way, we see that there's a much greater ratio of turbulent velocities to cold rotational velocities in these disk galaxies. And that's what's shown here on the right. Basically, the velocity dispersion in the interstellar medium increases as you go out to redshift 2. So typically you can see velocity dispersions of 50 to 100 kilometers per second. So an order of magnitude higher than what would be observed in a disk galaxy today. And so one of the really interesting questions is, what is the origin of this turbulence in these high redshift disk galaxies that makes them look so different from today's disk galaxies? Another interesting feature of these redshift 2 galaxies is their exchange of material with the circumgalactic and intergalactic medium. So when we look in the spectra of high redshift galaxies, we very commonly see the kinematic features of a large scale outflow. Okay, so if we look down here, okay, so these are velocity plots of a bunch of rest UV interstellar absorption lines in redshift 2 star-forming galaxies. And so the 0 point of the velocity field is indicated by this dotted line. And these curves here show the velocity profile of the interstellar absorption lines. Okay, and what you can see is that the centroid of the absorption lines is blue shifted by a couple hundred kilometers per second relative to 0. Okay, and this is the kinematic signature of an outflow. And this signature is detected in almost all redshift 2 star-forming galaxies that we observe. Furthermore, there doesn't appear to be a correlation between the shift that we see and the galaxy inclination in cases where we have Hubble imaging. And so what's interesting is that while if you go to a conference about gas in galaxies, you will typically see an image of M82, one of our neighbor galaxies, which has a very well-defined, bipolar outflow. But the fact that these kinematic signatures are so commonly detected in these redshift 2 star-forming galaxies suggests that perhaps the outflows are not as well collimated as they're seen in local galaxies, which may be connected to the geometry of the disks and the disks being less dynamically cold. Okay, so I think that's sort of an interesting thing to keep in mind, is our picture of what an outflow looks like. These high redshift outflows may not look like the M82 bipolar outflow. Okay, another feature that I want to mention is that the gas content in redshift 2 galaxies is high. This is connected with the high rate of star formation in galaxies of fixed mass. So CO observations of redshift 2 star forming galaxies suggest typical molecular gas fractions of greater than or equal to 50%. You can see here, again, from this review by Forster, Schreiber, and Weitz, that at 10 to the 10 solar masses, you can see this is this yellow curve. This is redshift 2. This is redshift 0.1. Okay, so the molecular gas fractions of main sequence star-forming galaxies in the local universe are an order of magnitude lower than what we see at redshift 2, or the redshift 2 galaxies have an order of magnitude higher gas fractions than what's observed locally. Okay, and furthermore, the molecular gas fraction at fixed stellar mass evolves steadily as we go from redshift 0 to redshift 3. Okay, so these are some of the features that I wanted to mention about the galaxy population in terms of its star formation activity, gas content, structural parameters, dynamics. Okay, just so you have this in mind as we start to talk about high redshift galaxies. Furthermore, I'd like you to keep these key questions in mind. So there are certain important questions that we consider when we think about the problem of galaxy formation and evolution. So one of the things we want to understand is how are stellar mass and structure assembled in galaxies? While we have a really good idea of the global progression of star formation in the universe as a function of cosmic time, we also want to understand what the physical processes are that drive star formation in individual galaxies. We want to understand how galaxies exchange gas and heavy elements with the intergalactic medium through accretion and outflow. And of course, we also want to understand the nature of the coevolution of black holes and stellar populations. And so today, I want to try to convince you that going back in time about 10 billion years to this early epoch that I've just been describing is ideal for investigating these questions, before the galaxy population has settled down and some of the important trends that are observed today are still being put into place. And the other really important thing is that I want to try to show you how rest frame optical spectroscopy is a very powerful tool for addressing these key questions of galaxy formation. Okay, and just a disclaimer, I'm not going to answer all these questions, but I do hope to answer at least one or two of them. Okay, so let's just make sure that we have a common vocabulary. When I talk about rest frame optical spectroscopy, today mainly I'm going to be speaking about emission lines, but we should also think about what the key set of absorption lines are. So on the top here, this is a spectrum of a local star-forming galaxy. And you can see here we are going from about 4,000 up to 7,000 angstroms. There's a suite of strong emission lines: oxygen 2, H beta, oxygen 3, H alpha, nitrogen 2, and sulfur 2. Okay, so these are some of the key emission features that we look at in the rest optical. At the same time, there are several key absorption features that we look at. So here, this is zooming in a little bit more on the spectrum. This is between 3,700 and 4,400 angstroms, but it contains many important features, such as the calcium K, H and K absorption lines. This is from a younger galaxy and a slightly older galaxy. If we go to longer wavelengths, there's the magnesium B absorption. There's also the so-called 4,000 angstrom break, which is a nice probe of the maturity of the stellar population. And so these features, these emission lines and stellar absorption lines, form the basis of what we would call traditional optical spectroscopy. And they provide key insights into the stellar and gaseous and dust contents of galaxies. But the thing is that at redshifts greater than 1.4, so going back into the redshift range that I'm talking about, the bluest of these features, this oxygen 2 emission lines, moves past 9,000 angstroms. And so our goal of studying them becomes a problem for near infrared spectroscopy. Okay. And so to assemble statistical samples of rest frame optical measurements, which was something that we wanted to do, what was really needed was a transformative boost in signal to noise and survey efficiency for near infrared spectrographs. And what I'll tell you about is that we were so fortunate that this happened about a decade ago, almost a decade ago, and enabled us to do all sorts of stuff using new instrumentation at the Keck Observatory. And also, just as a personal note, I want to say that it gives me great pleasure to be giving this talk with Max Bettini in the audience, because Max was really the pioneer of making these rest optical spectroscopic measurements for galaxies during the peak epoch of star formation. And he taught me basically everything that I know about rest optical spectroscopy, and he did it first. And so it's really exciting to be here with him today. Okay. So what I want to do for the rest of the talk is I want to tell you about our project, the MOSDEF survey, where the goal was to use rest optical spectroscopy to address some of the key questions of galaxy formation. And specifically, I want to focus on the science of the baryon cycle of galaxy formation at high redshift, so basically how gas goes into and out of galaxies, and then finish up just by saying a little bit about where we hope to take this in the future. Okay, so the requisite description of our survey. So with my friends in the University of California, many years ago, we were thinking about, what would be important for conducting a census of the galaxy population during cosmic noon. What do we need? And so, as we considered, what would be required to really do a good job on, surveying the high redshift galaxy population, we said, okay, it's important to have rest frame optical spectroscopy covering all of the strongest rest frame optical emission and absorption features at 3,700 up to 7,000 angstroms. So there's a spectra that I was just showing you before. Furthermore, we realized that we needed a large sample of objects spanning the full diversity of stellar populations. So now large, of course, is all relative. And what was really interesting is that there was so much discovery space that was available for studying high redshift galaxies in the rest frame optical when we were thinking about this. So really the sample of high quality rest optical spectroscopic measurements that existed a decade ago was in maybe the vicinity of 100 with very limited wavelength coverage. And so we knew that if we could just assemble a sample of an order 1,000 objects, this would represent an order of magnitude and a transformative boost in what was out there and enable us to do so much more than what was possible before. Furthermore, we wanted to look at multiple redshift bins at high redshift to enable evolutionary studies, even within these early times. And so we designed the MOSDEF survey with these goals in mind. And I think, as you'll see, we've really satisfied all these goals. Now, sort of crucial for carrying out this project is this beautiful instrument called MOSFIRE, the multi-object spectrometer for infrared exploration, which is at the Keck Observatory, and it was built at UCLA and Caltech by Ian McLean and Chuck Steidel. And so MOSFIRE enables near infrared, i.e. 0.9 to 2.5 micron spectroscopy over a 6x3 arc-minute field of view. You do one near infrared band at a time, so Y band, J band, H band, or K band. Now, one of the things that's really spectacular about MOSFIRE is its multiplex advantage, okay? So you can do up to 46 slits at a time with MOSFIRE using what's called the configurable slit unit, which enables you to make your slit masks almost in real time. The nominal spectral resolution for MOSFIRE using a 0.7 arcsecond slit, which is what we typically use for high redshift galaxy observations, is 3,500, so better than 100 kilometers per second. And MOSFIRE was commissioned in the spring of 2012 on the Keck 1 telescope. And so since then, it's been enabling measurements of rest frame optical spectra for galaxies at Z of 0.5 to 5, also rest frame UV spectra for galaxies up to Z of 8 and beyond. So MOSFIRE is just amazing. This shows you actually some raw data. This is unfortunately not high redshift galaxy spectra. This is just a spectrum of the sky, which is our main contaminant. But you can just see what a two-dimensional frame looks like off the telescope. If you want to see like one step further in data processing, which is basically just the subtraction of two frames that have been chopped, you can see the data with the emission line and it's negative. This is just from several minutes of observation time. And so the key thing to keep in mind about MOSFIRE is that it boasted a sensitivity boost of at least a factor of 5 relative to the previous Keck near-infrared spectroscopic instrumentation. So the instrument was called NIRSPEC, not to be confused with the JWST NIRSPEC, which has a different set of lowercase and capital letters, but that was a long slit spectrograph that Max and I got to use a lot a while ago. And so the thing about MOSFIRE is that so just, for an individual galaxy, the emission line sensitivity that you obtain is a few times 10 to the minus 18 ergs per second per centimeter squared in 2 hours. And so if that number means nothing to you, which it may, that flux level corresponds to a star formation rate of about 1 solar mass per year at redshift 2. So that means you could look at Milky Way levels of star formation in just a couple hours. So while in principle, one can do up to 46 objects at a time, in practice, typically when we design a MOSFIRE mask, we get on order 30 to 35 slits at a time. But still, if you think about the boost in sensitivity times the multiplex factor, the survey efficiency of MOSFIRE compared to the previous instrumentation is an increase of more than 2 orders of magnitude. Okay, and this is what was game-changing about MOSFIRE compared to the previous instrumentation. It enables us to start getting a census of the galaxy population rather than doing 1 at a time or 2 at a time. Okay, so that's MOSFIRE, and basically that's the jewel in our survey, and for many of us, MOSFIRE has just been really transformational. And I want to tell you a little bit about our project. Okay, so I already mentioned my collaborators. There are 6 of us who are the co-PIs of this project. We were awarded almost 50 nights of observing time between 2012 and 2016. And we targeted galaxies in HST legacy extragalactic fields. Okay, so why did we do that? Well, we wanted to look in fields where there was a wonderful multi-wavelength data set that already existed, okay, upon which we could add our MOSFIRE spectra. So we're basically leveraging this wonderful data set spanning from the radio through the X-rays and adding our MOSFIRE spectra, also including HST imaging. So we have information about the structural properties of galaxies as well as their multi-wavelength properties and their AGN properties and their stellar populations. The main redshift ranges in which we conducted our survey were redshift 1.4 to 1.7, 2.1 to 2.6, and 3 to 3.8. So we're looking at 9 to 12 billion years ago. This shows the redshift distribution of the survey. So we targeted 1,500 galaxies. Half of them were at redshift 2 because that's kind of our sweet spot. And we measured 1,300 redshifts. So we were very efficient in terms of our spectroscopic success rate. In terms of the target selection, the survey is H-band magnitude limited. This is somewhat in analogy to local redshift surveys, which are limited in terms of rest frame optical luminosity. Yeah, okay. Now, one thing to keep in mind is why did we look in these discrete redshift ranges? And this is just, this is one of practicality in our atmosphere. We selected our redshift ranges for the MOSDEF survey to optimize the detection of rest frame optical emission lines within windows of atmospheric transmission, or within the range of the near infrared filters. You can see, as I mentioned, our sweet spot is redshift 2, where oxygen 2 falls in the J band, H beta and O3 fall in the H band, H alpha, nitrogen 2, and sulfur 2 fall in the K band. And we have sort of analogous sets of lines for redshift 3 in the H and K band, and for redshift 1.5 in the Y band, J band, and H band. Okay, but unfortunately, the atmosphere means that we can't survey things continuously across all redshifts if we want to measure multiple rest optical emission lines. Okay, I wanted to show you some of the redshift 2 spectra from our survey sweet spot. And so in each one of these panels, we have the 2-dimensional J-band, H-band, and K-band spectrum. Below that is the 1-dimensional spectral extraction. And then below that is the multi-wavelength broadband spectral energy distribution spanning from the rest UV to the rest frame near infrared. And these are arranged in order of decreasing rest UV to rest optical ratio, or basically increasing galaxy maturity, right? So here you have a very young galaxy with a high specific star formation rate. And as we move from here to here to here to here, you can see the galaxies are getting redder and more evolved. The most extreme example here, which I'm not going to talk about in any great detail, but Mariska Creek wrote a Nature paper about this. This is one of the brightest galaxies in the sample. And you can see that in this galaxy, we actually detected stellar absorption lines. This is a quiescent galaxy, redshift 2, from which you can determine the stellar abundance pattern, which is really kind of cool. But for the most part, we're studying the emission lines in these galaxies. And if you look closely, you can see that the spectrum of the youngest galaxy, if we look at H alpha and nitrogen 2, you can see that the ratio here of nitrogen 2 to H alpha is very low. This is a young, less evolved galaxy. And as you go to the more evolved galaxies, here you can see this galaxy has high N2 to H alpha. It's more massive, more evolved. And so there's a connection between how the rest optical spectra look and also how the broadband SEDs look. And we'll get back to that in a little bit. Okay, let's see. I think that's all that I wanted to say about that. Okay, so now what I want to talk about is what we actually learn when we study the spectrum, the rest optical emission line spectrum of a galaxy. So of course, in an ideal world, like what you'd want to do is study all the individual H2 regions in a galaxy, either nearby or at high redshift. Emission lines provide a powerful probe of the properties of star forming regions. And so locally, it's possible to obtain long slit spectra for individual H2 regions. This is a schematic of a galaxy that was surveyed by the CHAOS survey, where you can put a slit on each H2 region. This is with like 35 parsec resolution. But of course, even in local galaxy surveys like the Sloan Digital Sky Survey, you're not probing individual H2 regions. So this is just showing some examples of galaxies from the Sloan survey with their 3 arcsecond diameter fibers trained on fibers of galaxies. And that's corresponding to a size of about 5 kiloparsecs at Z of 0.1, okay, for SDSS. Sort of in the same vein, when we have our MOSFIRE 0.7 arcsecond slit, okay, that goes across our star-forming galaxies at redshift 2, we're also probing regions of roughly 5 kiloparsecs across. And while some of our spectra we analyzed in the context of spatially resolved measurements, for the most part, we're looking at just integrated measurements of the galaxies. So the question is, when you have a spatially unresolved spectrum of a star-forming galaxy, which is the majority of the spectra at high redshift, the emission that falls in the slit is the galaxy integrated quantity. So this is the surface brightness weighted ensemble average of all of the H2 regions in diffuse ionized gas in the galaxy. Okay, and that's what I want you to keep in mind when we talk about some of the things that we're learning from these galaxy spectra. So what can you learn from a rest optical spectrum? So there's lots of stuff that you can learn from one of our MOSFIRE spectra. So for example, so here we have the J band, the H band, and the K band, and some of the key features that we're covering. So if you look at the ratio of Balmer lines, okay, that tells you about the dust extinction in the interstellar medium. If you then take that dust extinction and you still look at the Balmer lines, you can dust correct H alpha, for example, and get an estimate of the instantaneous star formation rate. As we'll talk about in a little bit, you can use different combinations of rest frame optical emission lines to learn about the oxygen abundance in the interstellar medium. If you look at doublets from oxygen 2 or sulfur 2, the ratios in these doublets are sensitive to the electron density in the interstellar medium. If you look at different ionization stages of the same element, like oxygen 3 and oxygen 2, so doubly ionized and singly ionized oxygen, this is sensitive to something called the ionization parameter. And the ionization parameter is defined as the ratio of the number density of ionizing photons to the number density of hydrogen atoms. And this contains information both about the ionizing source and also the geometric distribution of the ionized gas. In practice, the ionization parameter determines the relative populations of higher and lower ionization states, but it's as we'll see, it's connected to things like the gas phase oxygen abundance. Now, if you've looked at something like a BPT diagram, or if you're one of the co-authors of that work, you also know that the rest optical emission lines tell you about the nature of the ionizing source, in particular, whether it's an AGN or massive stars. Okay, so these patterns of emission lines are also sensitive to whether there's AGN activity. And with a spectrograph like MOSFIRE, which has at least moderate spectral resolution, you can actually use the profiles of the emission lines, like the profile of H alpha, to both look at virial kinematics, so use the velocity dispersion to look at the motions of ionized gas in H2 regions and get estimates of the dynamical mass of the galaxy. Or you can even look in more detail at the profile and decompose it to a narrow and broad component and analyze the broad component in terms of non-virial stuff like outflows of material from the galaxies or the broadline region of an AGN. Okay, so hopefully you get a flavor of the rich set of information that's contained in these rest optical emission line spectra. And of course, this is only part of the story because there's also wonderful stuff that's contained in absorption lines that we typically don't have the signal to noise to look at. All right, So as you know, hopefully you can see that if you have these spectra, there's all sorts of science that you can try to address. You can look at star formation, the growth of galaxies, dust attenuation, metallicities and the physical conditions in star forming regions, the cycle of baryons, so how gas goes in and out of galaxies, the dynamical masses and structural properties of galaxies, AGN accretion and the coevolution of black holes and galaxies. Even as I mentioned, you can look at stellar abundance patterns and the assembly history of galaxies and more. There's even more stuff that you can do with these spectra. So we've been busy. We've published about 40 papers from MOSDEF. And another thing that I want to say that I'm really excited about is that we actually just made all of our 1D and 2D reduced spectra available here. So if you go to the MOSDEF website, you can actually just download all of our reduced data and have fun yourself. So yeah, so the data have been released. Okay, but what I want to spend the rest of the talk on is looking at the metallicities and the physical conditions in the H2 regions of these distant galaxies. And this is where I want to highlight the work of Ryan Sanders, because we've been able to use these measurements of metallicities to actually try to say stuff about the nature of the cycle of baryons in galaxies at high redshift. Okay, so let's do that now. Okay, so when I talk about metallicity for the rest of the talk, I'm going to be referring to the gas phase oxygen abundance. In general, of course, metallicity refers to the abundance of heavy elements relative to hydrogen. And the key point here is that when you look at the gas phase oxygen abundance in a galaxy, this will reflect the integral of past star formation, but also gas flows into and out of the galaxy. So if we consider the first part, the integral past star formation, this is just a cartoon from my intro undergraduate class for non-majors, but this is just, you know, just to remind you, right, you know, you have gas cooling and forming stars. And then of course, you know, there's nuclear fusion in the stars. Stars die in various ways. The interstellar medium gets enriched, right? And then we have the next cycle of star formation. And so you can see that the enrichment in the interstellar medium and future generations of stars reflects the history of past star formation. But galaxies are not closed boxes, as we know, right? So this is a snapshot of a cosmological simulation of a galaxy forming. So you can see that, you know, gas accretes and cools and forms into stars. Then there's stellar feedback and gas gets ejected, okay? But this is a map of just hydrogen gas cooling, accreting and cooling into galaxies. But of course, what you need to remember is that metals are part of this story, okay? So the accreted material may have some metals, probably not that much, it's probably low metallicity. But then we have metals that are being fused inside stars and in supernova explosions, and then metals get ejected through outflows that we observe in the galaxies, okay? So the metal content in the galaxy is reflecting the star formation, but also the gas inflow and outflow and the balance among these processes. And indeed, a proper description of the accretion and outflow of gas in galaxies remains, I think, one of the outstanding frontiers for the study of galaxy formation, and one of the parts that we still need to do a lot of work on. So not only is it important to measure the metallicities of galaxies, but it's seen that the variation in the metal content of galaxies as a function of their stellar mass will provide important constraints on the processes of inflow, outflow, and star formation. And so specifically what we have the mass metallicity relationship, which I'll abbreviate as the MZR through the rest of the talk. So this is the oxygen abundance versus stellar mass. Probably the most famous compilation of this is from Tremonti et al. 2004 from the Sloan Digital Sky Survey. This is 53,000 galaxies. And it turns out that the form of this relationship will give you important constraints on, let's say, for example, how the mass loading factor of an outflow depends on the mass of a galaxy. So the mass loading factor is the mass outflow rate divided by the star formation rate. And it's one of the key components of, you know, our description of galaxy formation. So, you know, just to sort of drive this home a little bit more, on the right here, I have a plot from a simulation. These are the Mufasa simulations by Romuald Dave. And you can see that one of the predictions from the Mufasa simulations is the form of the mass metallicity relationship at redshift 0, and also over a broad range of redshifts, so the evolution of the mass metallicity relationship. And this mass-metallicity relationship, its slope and its normalization, also its scatter, are produced in the simulation under a certain set of assumptions about gas flows, okay? And so if we can make measurements of the mass-metallicity relationship and its evolution, we should be able to provide important constraints on, the baryon cycle through galaxies. And so the question is, well, how do we actually measure the metallicities of distant galaxies? How do we do this? And so in an ideal world, we perform what we call direct metallicities. And so you estimate a direct metallicity by measuring the strength of a strong emission line from oxygen, like oxygen 35007, and a weak auroral feature like oxygen 34363. The idea here is that the 5007 line comes from this energy level down to the excited ground state, whereas the 4363 level comes from this higher level into the intermediate level. So the relative population, the relative strength of those emission lines tells you about the populations of this upper level relative to the intermediate level, which is sensitive to the temperature of the gas. And if you have a constraint on the temperature of the gas in H2 regions, it allows you to convert the observed emission line strength of oxygen 35007 relative to a bomber line like H beta into an actual abundance of doubly ionized oxygen relative to hydrogen ions, okay? And so this is what we call the direct method, and this is inferring the oxygen abundance based on what I'd say physics. But most of the time, we actually can't measure these weak auroral lines, especially at redshifts greater than 1. This is very hard. And so we estimate the oxygen abundance in star-forming galaxies with calibrated ratios of strong emission lines. And this is what I call the method based on astronomy. Anyway, and so most famously, I think this was demonstrated in Pettini and Pagel 2004, where you have on the vertical axis here direct oxygen measurements for nearby H2 regions. And on the x-axis here, we have the empirical measurement of a strong emission line ratio. So emission lines that are easy to measure, like nitrogen 2 and H alpha, or oxygen 3 and H beta, and nitrogen 2 and H alpha. And what you can see is that there's a strong correlation between the ratios of these strong emission lines and the direct oxygen abundance. And so the idea is that you can measure the relationship between the physical quantity, the direct metallicity, and the strong line ratio for either nearby star-forming regions, or this was also done recently by Mirko Kurti for nearby galaxies. So here we have the strong line ratio on the vertical axis and the direct metallicity on the x-axis. And so you calibrate the strong line ratio to the physical quantity, the direct metallicity, and then you can take your measurement, it's easy to make, the strong line ratio, and convert it into an oxygen abundance. Another method is to use photoionization models that make predictions of this translation between the strong line ratio and the physical quantity oxygen abundance. And down here is a rogues gallery of some of the strong line ratios that we use for inferring oxygen abundance into O3, into O2, R23, O32. It's basically just different combinations of the rest optical emission line ratios. Okay, so before we delve into these physical properties, let me just say something empirically about what we see in high redshift galaxies. So just empirically, we see that the nebular excitation is higher at redshift 2 to 3 than it is at redshift 0 for galaxies of the same mass, okay? And empirically, the measure of excitation I'm talking about is either the O3 to H beta ratio or the O3 to O2 ratio, okay, which are telling us something about the excitation and the ionization parameter in these galaxy, the ionized ISM. And so here you can see a plot of O3 to H beta versus stellar mass, O3 to H beta versus stellar mass. In all these plots, the gray 2D histogram is Sloan galaxies at redshift 0, and the colored points are high redshift galaxies at either 2 or 3. And you can see that the high redshift galaxies have higher O3 to H beta at a given stellar mass. Down here, we have this from Ryan Sanders's work, the O32, so O3 to O2 versus stellar mass, same deal, where it's like offset towards a higher O3 to O2 at the same mass. You can also see there's an anti-correlation. As you go to higher mass, the O3 to O2 ratio goes down. And a simple explanation is just that galaxies have lower metallicity at fixed stellar mass as you go to higher redshift, and lower metallicity is typically correlated with higher excitation and higher ionization parameter. And that's largely the context in which we will be interpreting this. But the question is whether there are additional factors that are boosting these rest optical emission line ratios at fixed stellar mass, or can we explain most of it through just the lower metallicities of these galaxies at higher redshift. Okay, so now just to look in a little bit broader range of these empirical signatures as a function of stellar mass. This is work from Ryan Sanders. So here we have stellar mass and just different line ratios. And each one of these plots, the green squares represent galaxies from the Sloan Digital Sky Survey. Okay, so as you go to higher mass, these line ratios, this is, for example, R23 or O32 or O3 to H beta. The point is that, as I was just saying in the previous slide, that empirically there's evidence for higher excitation, higher ionization parameter, lower nitrogen to oxygen ratios at fixed stellar mass at redshift 2 relative to redshift 0. Okay, but if you use a good set of calibrations between the strong line ratios and metallicity, oxygen abundance, you can translate this into the actual mass metallicity relationship and its evolution. And that's what Ryan did over here. So you have oxygen abundance versus stellar mass. These green squares are the redshift 0 relation. Okay, these blue squares are redshift 2, the red triangles are redshift 3. Okay, and so we infer that the mass metallicity relationship evolves towards redshift 2 to 3, such that at fixed stellar mass, the redshift 2 to 3 galaxies have lower metallicities by about 0.3 to 0.4 dex, okay, at fixed stellar mass. And this is a fairly uncontroversial statement. It's been observed by many others that the mass metallicity evolves towards lower metallicity at fixed mass as you go to higher redshift. So the question is why? What is going on? Just as a little fun aside and as a little harbinger for JWST observations, accidentally in MOSDEF, we measured the metallicity of a galaxy at redshift 4.4. That was kind of fun. You can see its spectrum in the K band. We measured oxygen 2 emission and neon 3. I think this is the first measurement of the rest optical based metallicity for a star forming galaxy at redshift greater than 4. As I said, again, it's a harbinger for JWST observations where this type of measurement will become routine, but right now it's not. And so we inferred the metallicity, it's about 20% solar, and we boldly put it on a plot of the mass metallicity relationship as a function of redshift with one galaxy, but people have been guilty of the same. So here we have metallicity versus mass. Here's our redshift 2 points, our redshift 3 points, and here's our redshift 4 point. But as you'll see in a sec, it's dangerous to use one galaxy as a proxy for the whole mass metallicity relationship. But anyway, as I said, this is fun because we're going to be doing this routinely with JWST all the way out to redshift 10. Okay, so now the mass metallicity relationship is a very important scaling relation that's observed at galaxies across cosmic time. But it turns out that a lot of the scatter in the mass metallicity relationship can actually be accounted for if you take into account the dependence of metallicity not only on mass, but also on the star formation rate of the galaxy. And this is something that's called the fundamental metallicity relationship, okay? And this was, so specifically, the sense is that for a galaxy of a given mass, if it has a higher star formation rate, that goes along with having a lower metallicity. If it has a lower star formation rate, that goes along with having a higher stellar metallicity. And this is from Minucci et al. 2010. So here we have stellar mass and metallicity, okay? And then the color coding indicates galaxies from lower to higher star formation rates. And you can see as you go at the same mass, as you move from lower to higher star formation rate, the metallicity decreases, okay? And this has been observed by many authors. Okay, so the question is, what is the fundamental metallicity? What is the FMR telling us? And what does it mean? Like, what is it? Why is this anti-correlation between star formation rate and metallicity observed at fixed mass? And so I think the easiest thing is maybe for me just to quote Ramil Dave in his paper from 2017. So the physical explanation for this second parameter correlations with star formation rate is that an increase in gas accretion will bring in metal poor gas while fueling new star formation. And conversely, a lull in accretion will result in an evolution more similar to a closed box that will raise the metallicity quickly by consuming its gas. And in this context, you can see this is a plot from this simulation paper where you can see that deviations towards higher star formation rate are accompanied by deviations towards lower metallicity. Okay, so this is an explanation for what might be going on with this fundamental metallicity relationship, that it's reflecting, this interplay between gas infall and star formation and also outflow. Now, There's been a lot of discussion about the fundamental metallicity relationship, the FMR. I'll just say FMR so I don't stumble, about whether it exists at redshift 0. I think it's pretty well established that it exists at redshift 0, but also whether it exists at high redshift and whether it stays constant, or whether this anti-correlation between star formation rate and metallicity evolves in some way. And what does this evolution or non-evolution tell us about the balance between accretion and star formation and outflow in galaxies? And so again, there's been much work and debate about the FMR and its evolution. And I think we have sort of, I think what's now the latest word on this. This is also from Ryan Sanders's work. And so this is the result from the redshift 2 MOSDEF sample. So here we have delta metallicity that goes along with this, and this is delta star formation. And you can see that we find a very definite detection of this anti-correlation between metallicity and star formation rate. So we see the star formation rate dependence of the mass metallicity relationship, the FMR. The question is it the same dependence that's observed at redshift 2 that's observed at redshift 0? Okay, so the question is, if you know the mass and the star formation rate of a galaxy, do you then know its metallicity? And so this is again the latest word on what we found. Okay, so here we have oxygen abundance versus stellar mass, and these circles here represent data from the Sloan Digital Sky Survey. Okay, so you can see here we go from lower to higher star formation at the same mass. Okay, and these squares and triangles represent our redshift 2 to 3 data from MOSDEF. And if you instead represent the FMR with a new X variable, which is the star formation rate minus some function, the mass minus some function of the star formation rate, and collapse the data into this relationship. So again, the dots represent redshift 0, and you can see that the redshift 2 and redshift 3 points fall on the same relation. Okay, so not only do we detect an anti-correlation between star formation rate and metallicity at redshift 2, but it's the same relation at redshift 2 and redshift 0, or sorry, redshift 2 to 3 and redshift 0. Okay, so it appears that this same relationship persists to redshift 3. All right, so let me talk a little bit about what this means. So first of all, I want to say that in order to make these plots that I just showed you, it was very important to think carefully about how to calibrate emission line ratios to metallicity, both at redshift 0 and at high redshift. Okay, if you use different metallicity calibrations and not the ones that we use based on thinking about this for many years, you'd actually get a different result. Even earlier work from our group, work by Troncaso et al. That found significant evolution in the FMR, I think just by using calibrations between line ratios and metallicity that were actually not appropriate for either redshift 0 or redshift 3. Furthermore, it's important to use uniform emission line sets at different redshifts. Now, if we can interpret our results as robust, and we look at the slope of the mass metallicity relationship and interpret it in terms of simple chemical evolution models, the slope of the mass metallicity relationship is sensitive to the what we call the metal loading factor in outflow. So this is basically a metallicity weighted mass loading factor. And what you can see is that we infer that this metal loading factor is in a decreasing function of stellar mass. Okay, so this is telling us something about the way that mass and metals are leaving the galaxies and how they are more efficiently leaving the less massive galaxies. Furthermore, it appears that this metal loading factor increases with redshift at fixed stellar mass. And also, if the metallicity of the outflow relative to the metallicity of the ISM is comparable, this is actually telling us about the behavior of the mass loading factor of outflows, which is one of these really important quantities in galaxy formation that's hard to constrain with direct observations of gas motions. So this is really fundamental to understanding galaxy formation. Furthermore, in terms of why galaxies at a given stellar mass have lower metallicity as you go to higher redshift, it appears to be driven both by the increase in gas fraction and also this metal loading factor at fixed mass. And so as you go to higher redshift, the metals in galaxies are more diluted by them being more gas rich, but also the metals are more efficiently removed by the outflows in these galaxies. So furthermore, the fact that we see the same FMR over this wide range of redshifts indicates that the gas fraction and this mass loading factor at fixed stellar mass and star formation rate they're not evolving at redshift 0 to 3, okay? So that basically, once you have the mass and star formation rate of a galaxy, that tells you about its gas fraction and the mass loading factor, okay? And it seems finally that galaxies are remaining close to the same equilibrium among gas inflow, outflow, and star formation over the last 12 billion years, okay? And that's what we infer from this non-evolution of the FMR. All right, so one of the things that we agonized about for years, really, and I think we're still agonizing about it a little bit, is really how to measure the metallicity. So now I've spared you most of the talk about some of the journey that we've gone on about measuring metallicities, but it is really important, actually, as we enter into this new era of near-infrared spectroscopy with facilities like JWST and Roman and Euclid. And so the question is, when you look at a nearby H2 region, and then you look at the map of ionized gas in a redshift 2 star-forming galaxies, is this analogous? Are they analogous? Can we actually use the nearby H2 region as a proxy for the integrated spectrum of a redshift 2 galaxy? As we'll see, probably not. But it's also worth keeping in mind that when you analyze the spectrum of an individual H2 region, that this is also not a good proxy for the integrated spectrum of a redshift 0 galaxy, which contains not only H2 regions, but also diffuse ionized gas that is characterized by a different set of ionization conditions, okay? And so that's also worth keeping in mind, is that people are typically approximating galaxies as, one giant H2 region, and it's just not appropriate. But part of our agonizing about how to measure metallicities in high redshift galaxies was based on some measurements we did of various excitation diagrams of high redshift galaxies. So in the local universe, this is the Baldwin, Phillips, and Turlovich diagram, BPT diagram, the O3 to H beta versus nitrogen 2 to H alpha. And here you see the sequence of star-forming galaxies, and here AGNs. Okay, so the star-forming galaxies follow this tight sequence here of increasing metallicity and decreasing excitation. But what's exciting is that when you look at redshift 2 galaxies, so this is a paper by Chuck Seidel, where you see the sequence of redshift 0 galaxies, and you can see that the redshift 2 galaxies don't follow the same excitation sequence. They seem offset towards higher O3 to H beta and N2 to H alpha. And we see this also in MOSDEF. Okay, again, here's the redshift 0 sequence, and these red squares indicate where the redshift 2 galaxies are. So the question is, what drives this difference in the properties of high redshift galaxies? Why do they not follow the local sequence exactly? Why are they offset from the median of the local sequence? And there are various factors that may be driving this in terms of the density of the H2 regions, the hardness of the ionizing spectrum at fixed metallicity, the ionization parameter, the ratio of nitrogen to oxygen. And we've been trying to figure out what's actually going on in these high redshift galaxies, because it has implications for how we convert strong line ratios to oxygen abundance, but it also has implications for understanding the interplay between stars and gas in these distant galaxies. So since I'm getting close to the end, I'll just try to say this quickly. We measured the densities in the ionized ISM in these galaxies, and they're an order of magnitude higher than what we see locally. So typically you infer electron densities of about 25 per cubic centimeter, and we find electron densities of 2 to 300 per cubic centimeter in these redshift 2 star-forming galaxies. But that turns out to be a subdominant effect. It turns out that the emission line ratios don't depend strongly on the electron density or the pressure, if you want to think about it that way. Now, this would be a subject of a whole different talk, which I don't have time to give, but the totality of the data we've been analyzing for the last several years, both in terms of the rest optical spectra, photoionization modeling, and also the rest UV spectra that's provided constraints on the nature of the ionizing stars in these galaxies, suggests that the reason that these redshift 2 galaxies lie here and not here is that they are characterized by a harder ionizing spectrum at fixed nebular metallicity, fixed gas phase oxygen abundance, because the stars in these young galaxies are alpha enhanced, so they have harder ionizing spectra, lower iron abundance for a given oxygen abundance. And we can actually use many different of our emission line measurements from sulfur and neon and oxygen and nitrogen that all paint the same picture of these galaxies being young with alpha enhanced stars. And that's what's actually driving this offset. Okay. But this is a problem, because it tells us that the high redshift galaxies are not perfect analogs, the low redshift galaxies are not perfect analogs of the high redshift galaxies. And so what we really want to do, rather than trying to rely on tweaking our local calibrations to convert our line ratios into metallicities, is we want to measure direct metallicities at high redshift. This is a bold proposition, but we want to do it. And we've actually already started doing it. So MOSDEF wasn't really designed for this, but we did detect an auroral line in a galaxy at redshift 3. Okay, this is a galaxy at redshift 3.08. And so we measured the auroral oxygen line and the strong oxygen lines, and we inferred the oxygen abundance for this galaxy. And based on one galaxy, it seemed like maybe the local calibrations weren't terrible, but Ryan Sanders compiled both a bunch of galaxies from MOSDEF and some in the literature, and found that actually it seems like the local calibrations are not appropriate for redshift 2 galaxies on average if you have their direct metallicities and their strong line ratios, that they follow a different translation. Now, the thing is, this was heroic, and you can see some of these significances are not that, not as quite as heroic as we hope, but the problem is that this is really hard to do from the ground, okay? So not only is there the sky background to contend with, but we have to worry about these windows of atmospheric transmission that leave only very narrow redshift range for measuring these weak auroral lines and all the strong emission lines that you need for measuring a direct oxygen abundance. For example, our best detection, this was this galaxy Z of 2.65, which had a 7 sigma detection of the auroral line, is not at a redshift where we can actually measure the other lines. And so it's useless from the standpoint of estimating a direct oxygen abundance, okay? And so we need to get past the atmosphere if we want to measure these direct oxygen abundances for a large sample of galaxies at redshift 2 to 3 and perform a direct calibration, a direct empirical calibration of distant galaxies and place the oxygen abundance scale on a really robust scale, okay? And so, of course, what do we need for that? Well, this is a perfect application for JWST, for the TAC that's meeting soon, just telling you. And so the idea is that you can very easily detect oxygen 3, 43, 63, and other weak auroral lines at redshifts greater than 2, and directly calibrate the metallicity scale at high redshift for the first time using a large sample of objects, and then really place the abundance scale on a robust footing. And that's what we're going to do next, to really, really pin down metallicities at high redshift. Okay, so I think I'm going to stop there. So hopefully what I've convinced you is that if you can measure lots of rest optical emission lines at redshift 2 to 3, this is crucial for untangling some of the key physical processes in galaxies. If you can measure oxygen abundance in galaxies over cosmic time, you can obtain important constraints on models of galaxy formation and the flow of gas through galaxies. We find that galaxies appear to be in the same equilibrium among inflow and outflow and star formation over the past 12 billion years. And I'll just close with one thought. I mentioned this a little bit before. As I said, we're going to enter this new era of near infrared or rest optical spectroscopy with JWST, Roman, and we need these measurements of direct oxygen abundance, and also, I didn't talk about this, but the spatially resolved properties of these high redshift galaxies, if we're going to truly capitalize on these rest optical spectra and not just have measurements of line ratios, but have real measurements of the physical properties of galaxies. So I'll stop there. Thanks.
Thank you, Alice. Okay.